There's one thing in physics that always makes me chuckle whenever I think about it. Most of us believe that if we keep shrinking matter forever, we'll eventually reach a point where everything becomes too tiny, too fragile, too chaotic for anyone to control anymore. It sounds reasonable, like holding a rock is easy, but trying to pick up a speck of dust with the tip of a needle is incredibly difficult. But then you look at what science has actually accomplished, and all that intuition shatters instantly. In 1981, the scanning tunneling microscope, STM, was invented, and suddenly humans could not only see atoms, but also touch them with an electric current, so delicate it's hard to believe. Then in 1989, IBM researchers dragged individual xenon atoms across a nickel surface, arranging them into the three letters IBM, as if spelling with giant boulders, except these boulders were smaller than the diameter of a human hair by a factor of 100,000. When you see that, a question arises. If humans can already manipulate the single atom, does something like too small to control even exist anymore? Or has nature itself set up strange rules to ensure matter can't shrink to the point of slipping beyond our grasp? The answer lies in the quantum world, where Heisenberg's uncertainty principle blocks us, where energy is quantized into discrete levels, where the standard model dictates how particles interact, and where the Planck limit marks the deepest edge of reality. When you step into this realm, you realize the problem isn't that matter is too small, but that nature doesn't allow it to get that small in the first place. To truly understand why nature doesn't permit matter to become so small that it gets out of control, we have to start with what seems like a simple question. What is matter? Not in the way we sense it with our hands, eyes, or intuition. Those solid rocks, tiny dust particles, familiar objects we picture as tiny marbles, but in the way science has been forced to define it after more than a century of nature repeatedly correcting us. It all began in 1897 when J. Thomson discovered the electron and proved that the atom wasn't a solid sphere, as Dalton's model had described. Then came Ernest Rutherford's gold foil experiment from 1909 to 1911, showing that most of the atom is empty space, with a tiny nucleus containing nearly all the mass sitting in the center. And in 1932, James Chadwick confirmed the existence of the neutron, completing the classical picture of the atom. But even though those discoveries revolutionized science, they still weren't enough to describe what matter really is. If you look deeper, you'll see that electrons don't move in neat circular orbits like planets around the sun. They exist as a diffuse cloud, a literal probability density. What we call an orbital is really just a map showing where an electron is likely to be found, not a path of motion. Even picturing the electron as a little particle is wrong. At the microscopic scale, electrons behave as waves, sometimes as particles, sometimes as both, and they never behave the way macroscopic intuition wants them to. And from here, matter begins to reveal its true form. When you enter the world of quantum mechanics, you're no longer allowed to say an electron is a particle or a proton is a tiny ball. Instead, you have to accept that everything, every particle, every force, every interaction is a state of energy in quantum fields spread throughout space. An electron isn't an object. It's a stable excitation of the electron field. A photon isn't a little light bullet. It's a ripple in the electromagnetic field. Protons and neutrons aren't even smaller. Marbles, they're dynamic composites of quarks bound by gluons, the energy glue of the strong force. Everything you once thought of as matter is just stable regions of energy in a deeper network of underlying fields. Once you accept this, you understand why the idea of matter shrinking to infinity doesn't fit reality at all. It's not because humans lack the tools, but because nature itself doesn't allow these energy states to contract arbitrarily. To describe the entire structure of matter, modern physics relies on an intellectual edifice called the Standard Model. This isn't a dry list of a few disconnected particles. It's the alphabet the universe uses to write everything. In that alphabet, there are 6 types of quarks, 6 types of leptons, gluons to carry the strong force, photons for electromagnetism, W and Z bosons for the weak force, and finally the Higgs boson, the missing piece confirmed in 2012 after nearly half a century of searching. Each particle isn't matter in the way you think, but a unit of vibration, a pattern of oscillation in the underlying fields. So saying matter can shrink to the point where it can't be controlled is like saying the vibration frequency of a guitar string can get so small it no longer produces music. It makes no sense, because the size of matter is defined by the very shape of those field oscillations, not by how much you want to squeeze it. To help you visualize this better and prepare for what comes next, keep this running metaphor in mind. Imagine the universe as a gigantic quantum factory. In that factory, no component ever stands still for a second. Electrons constantly oscillate. Quarks swirl inside protons like bound streams of energy. Photons race like signals, carrying information between regions. And it all happens according to fixed rhythms that nature programmed long ago. The strange truth is, in this quantum factory, stability doesn't come from stillness, but from the dynamic balance of vibrations that never stop. Each particle is a stable chain of oscillations, like a sustained note in the harmony of quantum fields. And like every musical note, those vibrations can't exist if compressed below their structural level. You can't shrink an electron the way you shrink a rock, because an electron isn't an object. It's a field state, and fields have minimum energy levels dictated by nature itself. This is the key to the entire journey. If matter is structured energy, and that structure has a minimum energy level, then its size also has a minimum limit. The deeper you understand this, the clearer it becomes that the notion of matter getting so small, it's uncontrollable, isn't a physical possibility. It's an illusion born from the wrong way we think about the small world. But to see more clearly why matter defies our intuition so profoundly, we have to be honest about one thing. All the intuition humans possess, from throwing a rock, swinging a hammer, to pouring water into a glass, was forged in the realm of millimeter, centimeter, and meter scale things. That intuition was molded by the experience of a creature living in the macroscopic world, where everything has a clear position, a clear path, a clear speed, and especially where two objects never occupy two places at once. But when you step down to the atomic scale, all those seemingly obvious things dissolve in just a few classic experiments. The most iconic is Thomas Young's double-slit experiment in 1801 with light. When light is fired through two narrow slits, instead of producing two separate bright bands as expected, an interference pattern appears, alternating bright and dark fringes like ripples of water overlapping. This suggested that light doesn't behave like tiny bullets, but like spreading waves. At the time, the experiment was shocking enough, but it wasn't until the next century that it revealed an even more terrifying and beautiful truth. Not just light, but matter itself behaves like waves. In 1961, the double-slit experiment was repeated with electrons, thanks to Claus Johnson's technique, and the result was almost beyond anyone's imagination. A single electron, fired through the slits, one at a time, still produces an interference pattern, as if it splits itself in two, passes through both slits simultaneously, and interferes with itself. Imagine a marble in your hand doing that. Impossible. But for an electron, it's not just possible, it's inevitable. And from here, human intuition officially surrenders. Because when a material particle can travel through two paths at once, the concept of path that we're used to using becomes completely unsuitable for the quantum world. It's like trying to use a New York City street map to describe the flight path of a bee. The map isn't wrong, but it wasn't designed to describe that kind of motion. Similarly, our intuition isn't wrong. It's just designed to function in the large world, not the small one. The double-slit experiment exposes a profound truth. Small-scale matter doesn't obey the rules our senses are familiar with. It doesn't move like large objects, doesn't exist like large objects, and most importantly, it refuses to be bound by our intuition. When an electron interferes with itself, it forces us to abandon the idea of where it is at a specific moment. When the interference pattern disappears, if we try to see which slit it goes through, it shows us that observation and existence aren't independent, but a strange dance between the measurer and the measured. And when the electron behaves like a wave in the experiment, but appears as a particle upon hitting the screen, it reveals that small-scale matter becomes something everyday language can no longer describe. It's both wave and particle, neither wave nor particle, but a probabilistic structure existing in a space our intuition can't reach. And the most important point is if an electron can pass through two slits at once, then every intuition we use to say, matter can only behave this way, or surely it can't be controlled, if it gets that small, becomes worthless. The entire intuitive system, built from macroscopic experience, is useless at the microscopic scale. This lays the foundation for the entire story we'll explore in the following parts. If intuition is wrong, then the question, can matter get so small it's uncontrollable, must be answered not by feeling, but by the very laws that produce the electron's strange behavior. And those laws, from interference, uncertainty, quantization, to quantum field structure, will show us what seems paradoxical. Matter can't get so small. It loses control, because the small world doesn't operate the way our intuition suggests, but according to principles so strict that once you understand them correctly, you'll see they leave no room for any infinitely small size to exist. This is why we must set our intuition aside for now and start over from the beginning, using nature's own operating rules, not our thoughts about nature. So if small-scale matter behaves like probability clouds, self-interfering waves, entities that never stand still, then what does control really mean in this world? The answer, though it sounds very abstract at first, comes from an extremely simple idea that mathematician and information engineer Claude Shannon laid the foundation for in 1948. To control any system, you must have information about it. Control isn't pressing a button, pulling a string, or pushing an object. Control is the process in which you know the system's current state, its possible states, what states it can transition to next, and you intervene at the right point to shift it to the state you want. Controlling an object, whether a car, a satellite, or an electron, means you have information about its structure, position, momentum, energy, and you use that information to act appropriately. No information, no control. As Shannon put it, information isn't data. Information is what allows you to reduce uncertainty. This reveals a profound truth. Control is taking the initiative over uncertainty. And the moment you look at small-scale matter through that lens, a big problem emerges. The smaller it gets, the harder it is to have information. If you want to control a car, you just need to know its position, speed, direction. If you want to control a clock hand, you just need to know if it's moving fast or slow. But if you want to control an electron, you can't have perfectly accurate information about its position. You can't. Nature doesn't allow it. You can't say the electron is exactly at this coordinate with exactly this velocity. along exactly this path, because to know where it is, you have to measure it, and measuring it destroys all information about its momentum. If you try to preserve momentum, you lose information about position. This isn't a device error. This isn't a technological limit. This is a natural limit, written directly into the structure of the universe, the rule of the game that matter has followed since the earliest moments of the Big Bang. And that brings us to an uncomfortable but necessary truth. You can only control small-scale matter if you have information, but the smaller the scale, the easier that information vanishes, the more easily it's obscured by the quantum world's background fluctuation. Imagine wanting to control a large rock. Easy. You can measure every millimeter, every gram, but to control an atom, you have to work with probabilities, wave amplitudes, states that are never static, and the moment you try to look too closely, forcing the electron to tell you where it is, the very act of looking disrupts its state, distorting the information before you can use it to control anything. This is why the quantum world has limits that the macroscopic world doesn't. At large scales, information can be measured directly, stored, and used without disturbing the object. But at atomic scales, measurement is intervention, and intervention is change. And when the state changes, the information you thought you had becomes outdated, no longer representing the system, meaning you can't control it in the direct way we're used to. And here's the really interesting part. This very fact makes saying matter can get so small it becomes uncontrollable, meaningless, because the moment you shrink matter below the level where information can exist, matter itself loses the ability to maintain a stable state. If you can't know where it is, can't know its configuration, can't distinguish one state from another, then you no longer have a system to control. You just have an unobservable, inseparable, indescribable set of vibrations, and something indescribable can't be called matter in the familiar sense. Therefore, information is the gateway to the possibility of control, and the quantum world sets a very clear limit. Information can't be known with infinite precision, so matter can't exist in an infinitely small form. At this point, when we've understood that control depends on information, and information depends on the ability to measure, we must confront one of the most uncomfortable truths physics has ever thrown straight in humanity's face. You cannot know everything about an elementary particle at the same time, and this impossibility isn't because your equipment isn't sophisticated enough. It's because nature doesn't allow you to know. This principle, laid down by Werner Heisenberg in 1927, is written as Olax L-Pop, but don't let the formula fool you. It's not a mathematical trick. It's a revolutionary statement. The more precisely you know a particle's position, the less you can know about its momentum. And the more precisely you know its momentum, the more you lose track of its position. This isn't a measurement problem. It's the nature of reality itself. In other words, nature doesn't allow matter to stand still in any absolute sense, because to stand still, you'd need to know both position and momentum perfectly, a condition the universe never satisfies. Imagine you want to observe an electron very closely. To see something smaller than the wavelength of ordinary light, you have to use higher energy photons, that is, light with very short wavelengths, like X-rays or gamma rays. But the higher the photon's energy, the greater the momentum it carries. And when that photon slams into the electron to illuminate it for you to see, it simultaneously knocks the electron out of its original position, distorting the very information you were trying to gather. That means to know where the electron is, you have to disturb the electron itself. And when you disturb the electron to know its position, you lose information about its momentum, the very thing needed to predict its future. This is a cruel bargain. Nature forces you to accept. To know one thing, you must give up the other. If you try to know both, you get neither accurately. And this is where the small world becomes truly strange. The closer you try to look, the more you disturb the system. The more precisely you try to measure, the more you skew the result. The more you try to shine light on a tiny particle, the more wildly it bounces in directions you didn't expect. And as you shrink the target of observation, the impact force of the measurement itself becomes gigantic relative to the system, like using a truck to measure the position of a grain of sand. This leads us to an important conclusion. As matter gets smaller, it's not just the space it occupies that shrinks. The ability to know about it shrinks dramatically, too. And when the ability to know shrinks to the point where it's no longer enough to distinguish one state from another, you lose any capacity for control in any meaningful sense. You cannot control something whose state you cannot define. You cannot control a process whose very process distorts the moment you try to observe it. But here's the interesting part, and the one many people miss, precisely because information is limited. Matter itself is limited. If matter could shrink to the point where both al-tox and al-top become meaningless, matter would no longer have a stable state in which to exist. There's no way to keep a particle there if knowing where breaks its state. There's no way to maintain structure if background fluctuations, guaranteed by the uncertainty principle, always blow apart every attempt to shrink further. This reveals a bold truth. The uncertainty principle doesn't just set limits on measurement, it sets limits on the very existence of matter. If you try to force matter smaller than nature allows, the electron won't sit still in a smaller region. It jumps out, oscillates more violently, and the system loses stability completely. There's no energy state to anchor it. There's no quantum configuration to contain it. There is no infinitely shrinking size in nature. The uncertainty principle is the barrier that keeps matter within an existence possible range. It doesn't just protect information. It protects the very existence of the material world we live in. And when you realize that, you see clearly why the question, can matter get so small, it's uncontrollable, is actually misdirected. Matter never gets so small. It loses control. Because if it got smaller than the point where control has meaning, matter would cease to exist, to be controlled. Nature has set a hard floor, and every material structure dances on that floor. No one is allowed to fall through. If the uncertainty principle shows us that nature always hides part of the information, then quantization shows us that nature is even bolder. It doesn't just hide, it locks every material state into fixed energy levels that no one can squeeze between. This isn't a limit of equipment, not a flaw in technology. It's nature declaring that some things simply cannot happen, no matter how hard you try. This idea first appeared clearly in 1913, when Niels Bohr proposed the atomic model that later became the foundation of quantum mechanics. Electrons can only exist in discrete energy levels. Like a person climbing stairs, can only stand on each step and never hover between two. The most important thing here isn't the often misunderstood picture of orbits, but the discreteness of energy, a feature completely absent in classical physics. And the moment you understand this, one of nature's big secrets suddenly reveals itself. Electrons don't fall into the nucleus, not because of some mysterious repulsive force holding them back, but because there is no lower energy level for them to fall into. They're already at the bottom of the ladder. They can't lower their energy below the ground state, so they can't get any closer to the nucleus. This means atomic size isn't something that can be changed arbitrarily. That size is locked by the energy structure. Electrons don't orbit the nucleus in neat circular pairs like the glossy models in old textbooks draw. Instead, they occupy a spatial region defined by their wave function, and the shape of that region is determined by the electron's energy level. When the electron is in the lowest level, we get the Bohr radius, a fixed number, independent of your will or any force you try to apply. No matter how much you compress hydrogen gas with enormous pressure or put it in strange environments, the electron still can't squeeze closer to the nucleus than nature permits. If you try to push the electron a little closer, you'll only force it to jump to a higher energy level, expanding its occupied region into a new wave function shape. You can compress mechanically all you want, but you can't compress quantum mechanically. Nature doesn't allow you to break this structure. When you see this essence clearly, you grasp an important truth. Matter cannot be shrunk infinitely because it cannot reduce energy infinitely. Every atom has a ground state, the lowest possible energy level, and there is no below that state. If you try to force an electron into a smaller space, you don't make it stable, you make it angrier. Compressing the wave function increases the electron's kinetic energy, and that effect makes the atom vibrate violently rather than shrink. If you keep compressing, the electron doesn't fall into the nucleus. It bounces out, escapes, or causes the entire atomic structure to collapse. Nature doesn't respond by shrinking. It responds by exciting. This is why electrons have a fixed spatial domain, and atoms have a hard size, not because electrons take up space like little balls, but because energy levels cannot be squeezed below their foundation. Imagine trying to shrink a musical note. You can't lower its frequency below what the string can produce. Try that, and the string snaps rather than the sound collapsing to a point. Matter is the same. Trying to force matter into a non-existent energy region doesn't create smaller matter. It destroys the material state entirely. Quantization is nature's declaration that matter has a natural size, a limit set by the nature of energy states. So when people imagine matter can shrink to infinity, they're applying classical thinking to the quantum world, a thinking incompatible with reality. There are no infinitely negative energy levels. There is no state smaller than the ground state. There is no material structure at sizes where the wave function can't stabilize. Nature stops every attempt to shrink at the quantum level, and it's precisely that stopping that allows matter to endure. If electrons could fall to infinitely negative energy, atoms would collapse instantly, molecules wouldn't form, matter wouldn't exist, and our universe would be nothing but a featureless sea of energy. But electrons don't fall, don't contract, don't vanish, because nature placed a minimum floor beneath them and declared this far and no further. And it's that declaration, not our technology. That's why matter cannot shrink infinitely. So is there an ultimate limit, an absolute barrier, not just for matter, but for the very space in which matter exists? The answer lies in one of the strangest, yet most important concepts in modern physics, the Planck length, a size so small it defies any intuition. This length, about 1/6 is named after Max Planck, isn't the size of a particle, isn't the distance between 2 points. It's the minimum pixel of space-time itself. Think of it this way, to make it easier. If the universe is a gigantic screen, then 1/6 n is the smallest resolution of each pixel that makes up that screen. You can't divide the pixel further. The screen has no smaller elements. And if you try to zoom below this level, you don't see more detail. You just see nonsense. But what's crucial here is the Planck length isn't a number we made up for fun. It's the scale where the three fundamental pillars of physics, quantum mechanics, special relativity, and general relativity, begin to contradict each other. Below 1/6 n, you can't meaningfully say, this is the position of point A, or this is the distance between A and B, because the background energy fluctuations of space-time become so violent that familiar concepts like position, distance before, after, near, far, all collapse. On the surface, this sounds like a mathematical problem, but it's actually the foundation of all reality. If you can't define position below the Planck length, then you can't have material structure below it. Matter needs shape to exist. Shape needs space. Space needs resolution. And that resolution has a limit. Below the Planck threshold, space-time is no longer smooth. As we imagine, it becomes a quantum foam, a seething ocean of violent fluctuations, where position and time lose meaning, an electron, a proton, or any structure that wants to exist needs a definable region of space. But if you shrink matter to the point where space itself is no longer definable, matter has no foundation to cling to. This is like trying to build a skyscraper on quicksand. Not that the building can't be smaller, but the ground is no longer stable enough to support it. And here's the key part. The Planck length doesn't say matter has a size of 10^1. It says you can't meaningfully say matter is smaller than or equal to that number in any way. If you ask, can an electron be smaller? The question becomes meaningless, not because matter refuses, but because smaller is no longer a valid concept. You can't shrink matter into a space where space itself no longer exists. Go back to the screen metaphor. If the smallest pixel is 1^1, you can't display a 0, 5^1, 5 image. Not because you're incapable, because the screen doesn't support it. Nature is the same. Space-time has its own hardware resolution. You can't draw matter smaller than that resolution, because there are no points left to draw on. Trying to describe structure below the Planck threshold is like trying to distinguish 2 points separated by 1,000th of a light wavelength. You can't, because light can't carry information at that resolution. The universe behaves similarly. Below the Planck length, no signal can distinguish 2 positions. That's equivalent to there being no 2 positions to distinguish. So when people ask whether matter can shrink infinitely, they're unwittingly asking a question that exceeds the capability of the very space-time foundation on which matter rests. Matter cannot shrink infinitely, not because some force pushes it back, or because quantum structure angrily explodes outward, but because space itself ceases to exist geometrically below a specific limit. At the Planck scale, all our concepts, surface, volume, distance, direction, vanish like mist in sunlight. And when the foundation vanishes, matter cannot exist. This is no longer a limit of matter. It's a limit of reality itself. If you tried to shrink an atom to a size below the Planck length, you wouldn't create a smaller atom. You'd create a meaningless question. Just like asking where is the westernmost point of a circle. There's no answer because the question is incompatible with the shape. Thus, the Planck length is the foundational barrier nature erects, a hard boundary where geometric language ends and the world becomes indescribable. And rightly so, if space cannot support smaller structures, then matter cannot be smaller. Not due to technical limits, not due to technological limits, but due to the limits of existence itself. Even in what is considered absolute stillness, matter never stops vibrating. This idea first emerged in 1907, when Albert Einstein realized that atoms in a crystal lattice must still have a minimum energy even at 0 Kelvin. By 1916, Walther Nernst developed this into the concept of zero-point energy. A bold claim, absolute zero, never equates to absolute stillness. And indeed, when you cool an object close to 0 Kelvin, you can reduce thermal motion, but you can never completely eliminate vibration. Nature doesn't allow it, because if matter stopped vibrating entirely, you'd know both position and momentum exactly. An absolute prohibition by the uncertainty principle. That very prohibition forces every atom to retain a ground state energy, a minimum vibration rhythm that no amount of heat removal can take away. Imagine trying to make a lake's surface perfectly flat by stopping the wind. The water may look flat, but at the molecular level, vibrations are always there, not due to the environment, but due to the quantum structure forcing them to exist. This has profound consequences. Atoms cannot shrink below a certain size, because if you try to compress the wave function into a smaller space, you force the electron into a state with higher kinetic energy, dramatically increasing oscillation amplitude, and the atom becomes unstable. 0-point energy, in a very real way, is the invisible barrier that stops every attempt to shrink matter beyond its quantum limit. You can think of it as a spring that never fully compresses. The harder you push, the stronger the restoring force. And at the atomic scale, that restoring force isn't classical mechanics. It's the surge of quantum kinetic energy. This is also why helium doesn't solidify at normal pressure, even at 0 Kelvin. The helium atoms vibrate so strongly that they slide past each other without enough time to lock into a crystal structure. And that ceaseless vibration is vivid proof that every atom possesses a minimum size that cannot be compressed below what nature dictates. If you stood before an atom and asked, "Can I squeeze you smaller?" the quantum answer is no, because I must always vibrate to exist. Background vibration is the energy floor that matter cannot penetrate, not because some mysterious force holds the atom back, but because the lowest energy state of the wave function isn't 0. It's a positive value that cannot be reduced further. If the lowest energy state was 0, the electron would fall straight into the nucleus. Atoms would collapse, molecules would vanish, and matter, in the familiar sense, would cease to exist. But nature doesn't allow that. Nature forces every particle to maintain its fundamental vibration rhythm, like background music that never stops. That rhythm is what sustains the structure of the universe. Thanks to 0-point energy, atoms have a minimum size. Thanks to minimum size, atoms don't collapse. Thanks to atoms not collapsing, matter doesn't vanish. And thanks to matter not vanishing, you have a world to stand in and ask these questions. And right here, you begin to see the bigger picture more clearly. Every force, every limit, every quantum law is quietly erecting absolute barriers so that matter exists precisely in the range where control still has meaning. Matter cannot stand still. Matter cannot be smaller. Matter cannot hide in space below the resolution of space-time itself. And all of that is not a restriction. It's the necessary condition for the world to keep the shape we live in. Once we've understood that atoms never stand still and always vibrate due to 0-point energy, we have to confront an even more perverse truth. In the small world, you cannot measure anything without breaking it. At the atomic scale, looking, touching, checking, determining, all of these are synonymous with interfering. This isn't a matter of being careful or having a steady hand. It's the fundamental nature of quantum measurement, and there's no clearer proof than the Stern Gerlach experiment of 1922, where physicists Otto Stern and Walther Gerlach sent a beam of silver atoms through a device that created an inhomogeneous magnetic field. Instead of spreading out continuously, as classical intuition would predict, the beam split into 2 distinct spots corresponding to 2 spin states, up or down. What was shocking wasn't the splitting itself, but the fact that the measurement forced the atoms to choose a spin state. Before measurement, spin exists as a free superposition, not fully committed to either side. But the instant you measure it, you force it to decide which side to stand on. Measurement doesn't record the state, it creates the state. And if you think this is just theoretical sleight of hand, imagine an everyday but ironically funny example. You want to know what state an electron is in. You approach, extend your measuring eye, and essentially you're tapping it with a photon. The electron once tapped is no longer the same electron. It gets knocked off course, spun around, momentum changed, or shifted to an entirely new state. It's like trying to find out the state of a tiny ant by gently poking it. You're not just looking, you're making it panic and scatter, then recording the result and calling it observation. But at the quantum scale, that humor becomes hard law. The harder you try to measure, the more you break what you're measuring. This imposes an absolute limit on control. When you want to control a large object, you can measure it freely. Measure wheel position, speed, direction of rotation, whatever you like. But when you want to control an electron, a spin, or a quantum state, you face the truth that measurement is never passive. It's always a sharp slap to the system. And that slap is strong enough to alter the future you wanted to control. Every quantum state is as delicate as a soap bubble. The moment you touch it to check if it's real, you've already popped it. Therefore, direct control of matter at sizes smaller than the stability threshold becomes impossible in principle. You cannot control a system if the very act of gathering information, the act necessary for control, destroys the system itself. It's like trying to steer a car whose steering wheel shatters the instant you touch it. The Stern-Gerlach experiment is just the simplest version of this. In reality, every quantum measurement has a coercive nature to know what state a particle is in. You have to force it to choose a state, to know spin direction. You have to force it to orient its spin. To know energy, you have to interact in a way that reveals the energy level. In every case, measurement isn't just observation, it's intervention. And because measurement intervenes, when you try to observe matter at sizes smaller than nature allows, you lose the ability to control. No reliable information remains. No stable state remains. No durable structure remains for you to act upon. All that's left is a system destroyed by the very act of measurement. This is why matter cannot maintain a state at sizes smaller than the quantum limit. There is no way for a structure to exist if every measurement collapses it. Nature doesn't just limit your ability to see, it limits the very existence of matter in spaces where measurement cannot be performed meaningfully. And since control requires information, and information requires measurement, that barrier is precisely why matter cannot shrink infinitely. Because below a certain point, measurement stops being observation and becomes destruction. So how can humans control individual atoms? How can we manipulate something so fragile without it instantly shattering in our hands? And this is the part that always delights me, because humans have found ways to manipulate matter using quantum rules, not by fighting them, but by following their rhythm. One of the most extraordinary tools we've ever created is the scanning tunneling microscope, STM. Instead of shining light on the sample like an optical microscope, the STM brings an ultra-sharp tip, just a few atoms at the apex, close enough to the sample surface that electrons can tunnel through the narrow gap via the quantum tunneling effect. This tunneling current is so sensitive that raising or lowering the tip by 1,000th of a nanometer causes a clear change in current. This allows us to scan the atomic surface the way a blind person runs their fingers over braille, feeling every bump and hollow of the atoms. But the STM doesn't just see atoms. It can push or pull individual atoms by adjusting the voltage between the tip and the surface. That's the technique IBM scientists used in 1989 when they arranged 35 xenon atoms into the three letters IBM. Picture the scene. On the screen there are just a few bright dots, each a single atom. They gently dragged each atom into position with the tip as if arranging pebbles on a beach, except these pebbles are about 100,000 times smaller than a human hair. Needless to say, it was an iconic feat. Humans not only saw atoms, but manipulated them like pieces in an ultra-tiny jigsaw puzzle. But the STM is only half the story. The other half comes from the atomic force microscope, AFM, which takes a different but equally magical approach. The AFM uses a tip mounted on a tiny flexible cantilever, scanning over the sample surface and measuring the attractive or repulsive forces between the tip and surface atoms. Any change in force makes the cantilever vibrate, and those vibrations are recorded to build a three-dimensional map of the atomic surface. Both STM and AFM allow us to touch the small world without breaking it, or more precisely, they touch in a way nature accepts, instead of touching with crude light that sends electrons flying. However, to control an atom, you don't just need a delicate enough hand. You also need to slow the atom down. Electrons vibrate violently due to the uncertainty principle. But atoms with greater mass can be slowed using a beautiful technique called laser cooling. In 1997, Stephen Chu and two other scientists received the Nobel Prize for developing a method that uses photons to push back against atomic motion. It sounds absurd. How can light cool something? But the secret lies in the Doppler effect. When an atom moves toward a laser beam, it sees the light as bluer, higher energy, absorbs the photon more strongly, and each absorbed photon acts like a tiny kick that slows it down. Repeated millions of times, the atom slows to near standstill by macroscopic standards. At that point, control becomes far easier. You can trap atoms with magnetic traps, optical traps, even put them in states where their motion is hundreds of times slower than the speed of sound. This enables manipulation with unimaginable precision. But as soon as you hear these miraculous stories, remember the most important lesson. All these techniques, SETM, AFM, laser cooling, operate within the range nature permits. They don't overcome the uncertainty principle. They don't overcome quantization. They don't overcome the Planck limit. We don't control matter smaller than nature allows. We only control matter up to the threshold where nature still defines its states. Go below that threshold, and every measurement becomes disturbance. Every structure becomes unstable, and matter ceases to be matter. The STM sees atoms, but cannot see half atoms. The AFM controls surface structures, but cannot control anything below the resolution of space itself. Laser cooling slows atoms, but cannot make them completely static. What makes the small world astonishing isn't just the limits nature imposes, but the fact that those very limits create stability for matter, preventing everything from collapsing into a meaningless point. When you look at atoms, molecules, solids, or even the chip running in your computer, none of it exists in spite of quantum mechanics. It exists because of quantum mechanics. If electrons could occupy any energy level, if they could fall forever into the nucleus, if nuclei weren't held by the strong force, if zero-point energy didn't enforce a minimum distance between atoms, there would be no wood, no metal, no water, no organic molecules, and certainly no life. Matter would collapse into tiny energy clumps and never form anything resembling stable structure. But fortunately, or rather inevitably, according to natural law, quantum mechanics steps in to protect the universe from that very collapse. Atoms have a minimum size because electrons cannot get closer to the nucleus than the ground state energy allows. Chemical bonds exist because electron orbitals combine into low but not zero energy stable configurations. And because electrons obey the Pauli principle, they cannot pile up infinitely, forcing atoms to arrange in ordered ways, rather than all collapsing to the same spot. That's why solids are hard. Liquids have viscosity. Molecules have three-dimensional shapes, and biology can self-organize. What's fascinating is that when you dive into solid-state physics, you discover that the hardness of diamond, the toughness of steel, the conductivity of copper, and superconductivity all arise from quantum rules, from electron distribution in crystal lattices to blocked energy levels, from electron-phonon interactions to band structures formed by the very discreteness of quantum systems. Even the most familiar thing in modern life, the transistor, is a direct child of quantum mechanics. Intel's first chip, the 4004, debuted in 1971 with transistors about 10 micrometers in size. Imagine a human hair sliced into tenths. That was transistor size back then. But today's transistors are down to 3 nanometers, millions of times smaller than a dust particle. So small that 30,000 of them lined up would barely equal the width of your fingernail. They work not because of traditional mechanical miniaturization, but because humans have correctly exploited quantum laws, designing energy bands so electrons flow only when needed and are blocked when not, controlling quantum tunneling, so electrons jump energy barriers at the right moments, using quantization to create clear on-off regions that computers can read. If transistors could shrink infinitely, energy bands wouldn't be discrete, electrons wouldn't be locked into states, and components couldn't operate on binary logic. The digital world we live in, phones, laptops, internet, AI, all rests on one ironic truth. Matter is small, but not too small. If quantum mechanics didn't stop electrons from falling into nuclei, we wouldn't have atoms. If Pauli didn't stop electrons from piling up, we wouldn't have solid structures. If band gaps didn't exist, we wouldn't have transistors. And if the small world weren't hard in the quantum sense, we wouldn't have nanotechnology, 3 nanometers chips, or the modern semiconductor industry. Thus, quantum mechanics isn't the villain making matter weird. It's the silent architect ensuring everything has shape. All the stability of the macroscopic world, trees, mountains, human bodies, is built on quantum barriers in the microscopic world. That's why we can control small matter, because quantum mechanics keeps it stable enough not to collapse. But quantum mechanics is also why we cannot control matter smaller than nature allows, because below that point, no stable states remain to control. Matter isn't clay you can squeeze infinitely small. It's a quantum symphony where every note, every energy state is predefined. You can play the symphony as you like, but you cannot add notes below the limit nature has set. When you begin to see clearly that quantum mechanics doesn't just impose limits, but also gives matter its hardness, you enter one of the most beautiful and strangest proofs of the microscopic world. Superfluid helium. If you want to see how quantum vibration keeps matter from collapsing, look at helium, an element that seems gentle but hides a secret that forced physics to rethink stability entirely. When you cool helium close to 0 Kelvin, something bizarre happens. Unlike every other substance, it doesn't solidify. You can put helium in a vacuum flask, lower the temperature to where all motion should supposedly stop, yet helium still slides through the bottom like a ghostly liquid, with no friction, no viscosity, and unable to be held in any corner. The reason isn't some oddity of helium. It's that helium atoms vibrate so strongly they cannot be locked into a crystal lattice. 0-point energy keeps them constantly bouncing around space, refusing to stand still long enough to form a solid structure. This is perfect proof of the quantum truth. Atoms always vibrate, even when you've removed every bit of heat possible. And paradoxically, that very vibration is what keeps matter from collapsing. Imagine trying to force 2 helium atoms right next to each other. What happens? They don't merge like 2 water drops. Instead, each atom's background vibration pushes them apart, not because some mysterious repulsive force suddenly appears, but because compressing the spatial region the atomic wave function occupies causes its quantum kinetic energy to surge, making the atom vibrate more violently and refuse to fit in a smaller volume. No atom in the universe stands still, And that very non-standing still is nature's strongest barrier against collapse. If you think about molecules, crystals, or any durable form of matter, you'll see the same rule. Atoms can only approach each other to a certain distance, the distance where attractive and quantum repulsive forces balance. Try to force them closer, and electron oscillation energy rises, quantum pressure rises, and the structure resists. That's why you cannot compress matter to infinite smallness. You cannot gather all the matter in the universe into a zero-size point, unless you have what's called a black hole. And even there, quantum theory insists that absolute collapse is something ordinary physics language cannot describe. At everyday scales, this means any matter you've ever touched, from the teacup on your table to the molecules in your brain, has a minimum size, not because of mechanical rigidity, but because quantum vibration forces it to have that size. If that vibration didn't exist, electrons would fall into nuclei, atoms would shrink to dimensionless points, and all matter would collapse into a meaningless energy blob. But because vibration is always present, atoms don't collapse. Matter doesn't collapse. The universe doesn't collapse, and you have room to exist. Strange, isn't it? What we thought was random jiggling turns out to be the foundation of stability. Try shifting your perspective. Zero-point energy isn't an annoyance. It's an invisible soft cushion, preventing the universe from crushing itself. It's nature's reminder. This far and no further. Any smaller is impossible. And so every piece of matter retains its minimum size, not due to mysterious forces, not due to luck, but due to the perfect balance between quantum constraints, background vibration, and space-time structure. That eternal vibration is why matter has shape, molecules have size, and atoms cannot be squeezed into infinitely small points. In a universe without zero-point energy, everything would collapse. In a universe with zero-point energy, matter stands firm. And that very firmness is why we have a world to control. A small, strange world, but one that never gets too small to vanish beneath our feet. If the quantum world is a factory, then chemical bonds are how nature assembles those vibrating bricks into structures with shape, hardness, and function. But what's fascinating is they don't snap together by touching like Lego pieces. They bond by overlapping wave functions. Let's start with a simple picture. When two hydrogen atoms approach each other, their electrons don't move like two balls trying to squeeze into the space between the nuclei. Instead, the two electron wave functions mix together, creating a new distribution region with lower energy. This region is called a sigma bond, a cloud of electrons lying between the two nuclei, holding them together like a seatbelt made of probability. If you want to picture it in everyday language, imagine two people holding a heavy blanket together. The more evenly and widely the blanket is stretched, the closer the two people are pulled. A sigma bond works the same way. It pulls the two nuclei toward a common center because the lower energy configuration is the stable one. And when you have atoms larger than hydrogen, the electron cloud doesn't just form sigma bonds. It can form pi bonds, a kind of quantum bridge lying above and below the nuclear axis, like two parallel cloud layers. Pi bonds create impressive structures like the benzene ring, or conjugated systems in organic molecules, where electrons aren't locked in one fixed spot, but spread out like current flowing in a closed circuit. But whether sigma or pi, every chemical bond follows the same principle. Electrons arrange themselves into spatial regions where the total energy is lowest, and from this simple principle, the entire material world is built. However, to understand the limits of small-scale matter, we have to pay attention to one crucial detail. Chemical bonds only exist at a specific distance. Two atoms cannot be forced right up against each other below a certain limit, not because the nuclei are big, but because if the wave function is squeezed into a smaller space than quantum mechanics allows, the electron's kinetic energy surges and the bond becomes unstable. That's why molecules have fixed bond lengths. Take the hydrogen molecule as an example. Its bond length is about 0.074 nanometers. You might imagine nudging the two nuclei a little closer, but nature immediately objects when you do that. The electrons don't crowd closer, as one might expect. They resist by increasing their energy and pushing the nuclei apart. It's like two people tied together with an elastic cord. Pull them a bit closer. The cord stretches and pushes back with greater force. Chemical bonds can be stretched, twisted, vibrated, but they cannot be arbitrarily compressed. Molecular structure isn't like a lump of clay you can squeeze however you want. It's an energy wave rhythm, and wave rhythms cannot be compressed below the spatial domain their equations permit. This completely shatters a common intuition. Many people think that with enough pressure, if we're strong enough, we could squeeze molecules smaller, force atoms so close together that we create ultra-dense matter. But chemical bonding isn't classical physics. It's not two hard objects bumping into each other. When you compress a molecule below its quantum limit, the molecule doesn't become a smaller version. It becomes unstable. The wave function distorts beyond the allowable threshold. Electrons jump to different configurations. Bonds break, and the molecular structure disintegrates. That's why there is no such thing as an infinitely small molecule. There's no way to pump pressure into the system to force bonds down to an arbitrary size. Nature has set the bond distance as an optimal energy domain, a deep valley in the quantum landscape. If you try to push the molecule out of that valley in the direction of shrinking, it simply climbs the energy slope and falls into a chaotic region where no bonds remain stable. And this is precisely why matter has shape. Water molecules have a 104.5 degrees angle. Methane is tetrahedral. CO high is linear. Benzene is flat. Every shape comes from the lowest energy state of the electron wave functions. You cannot squeeze a benzene molecule into a tiny version while preserving its properties. It would become something entirely different or cease to exist. Electron density, vibrational energy, bond lengths, all are quantized. Molecular size, therefore, isn't a variable. You can adjust at will. It's the result of a powerful balance between bonding energy and quantum repulsive energy. And when you understand this, you'll see more clearly a truth that runs through everything. Matter can only be as small as the point where electron wave functions can still form stable configurations. Go below that size, and the world doesn't shrink. It collapses into chaos. It is precisely in chemical bonds, in the way these vibrating bricks assemble into molecular architecture, that we once again see nature does not permit infinitely small matter. It only permits matter to be small enough to exist, no smaller. And what determines the size of an atom? Why is a hydrogen atom about 0.1 nanometers across and not 1 nanometer or 104 nanometers? Why does nature choose this size and not allow it to change? The answer lies in the magical balance between two powerful but opposing forces. The Coulomb force pushing electrons away from the nucleus, and the strong nuclear force holding protons and neutrons tightly in the core. Let's start with the more familiar one. The Coulomb force. Electrons carry negative charge. The nucleus carries positive charge. And everyone knows opposite charges attract. If that attractive force were the only one, you'd think electrons would plunge straight into the nucleus and stick to it like magnets on a fridge. But electrons don't behave like marbles. They are diffuse wave functions. And when you try to squeeze the wave function into a smaller spatial region, its kinetic energy surges dramatically due to the uncertainty principle. This creates a real but virtual quantum repulsive force. The closer you force the electron to the nucleus, the more unstable it becomes, the more violently it vibrates, and the higher its energy rises, until there's no longer any benefit to moving closer. This is why electrons don't fall into the nucleus. The Coulomb attraction wants to pull them in, but quantum kinetic energy wants to push them out. The balance between the two creates the atomic radius. Imagine pulling on a rubber band. Pull too lightly, and the tension isn't enough to hold the object. Pull too hard, and the band snaps out of your hand. There's a balance point where the pulling force and tension cancel each other. An atom is the same. It has a harmony point where Coulomb attraction and quantum repulsion perfectly cancel, creating a stable size. And that's why a hydrogen atom is about 0.0529 nanometers across, the famous number called the Bohr radius, not because the electron likes being at that distance, but because nature doesn't allow it to be anywhere else, stably. But Coulomb only handles the electrons. Inside the nucleus, an even bigger battle is taking place. Protons all carry positive charge, and by Coulomb, they should repel each other so violently that the nucleus would explode instantly. If electromagnetic repulsion were the only force in the nucleus, no atom larger than hydrogen would exist. Even hydrogen wouldn't be stable. So what holds the protons together? The strong nuclear force, a colossal force, almost unimaginable. Dozens of times stronger than the electromagnetic force, but operating over an extremely short range, about 1 femtometer. Within that range, the strong force glues protons and neutrons together, like super-energy glue. But the instant you step outside that range, the force vanishes so abruptly. It acts like an on-off switch. It's the strong force that gives the nucleus its stability and sets its fixed size, about 100,000 times smaller than the entire atom. When you put these two stories together, the Coulomb force and quantum repulsion for electrons, the strong force and electromagnetic force for protons, you begin to see a beautiful picture. Atomic size isn't accidental. It's the result of a delicate balance among nature's forces. Outside the nucleus, electrons are tugged in two directions. Coulomb attraction pulls inward, and quantum kinetic energy pushes outward. Inside the nucleus, protons are torn apart by Coulomb repulsion, but squeezed together by the strong force. Both layers of structure seek the lowest energy equilibrium point, and that point is the size of the atom. And what's remarkable is that this size is stable to the point of punishing any attempt to change it. You cannot squeeze an atom smaller, because when you do, electrons increase their kinetic energy, the wave function swells outward, and the atom resists by expanding back. You also cannot stretch an atom infinitely large, because Coulomb force pulls the electrons back. Nature has set a single correct point, and the atom exists at that point, no more, no less. This is precisely why there are no physically smaller atoms. You can create ions, strip electrons away, alter chemical structure, but you cannot shrink atomic size below the quantum threshold. It is fixed by the balance between attraction and repulsion at the most fundamental level of the universe. And when you look at this, you'll see that the question, can matter be smaller, has never really been on the right track. Matter is as small as nature permits, and no smaller. Atoms have size because the forces want them to have that size. The space of electrons, the range of the strong force, the anti-collapse resistance of quantum vibration, all harmonize to produce the roughly 0.1 nanometers we call atomic size. That's not luck. That's the inevitability of physical laws. Just when you think the force balance between electrons and nucleus is the deepest layer of material structure, nature lifts another curtain, revealing something even stranger, even vacuum. What intuition tells us is nothing, never stands still. Vacuum isn't a meaningless empty void, not a cold inactive nothingness. It's a continuously fluctuating electromagnetic field, vibrating even in its lowest energy state. You might think that if you remove every photon, every particle, every vibration at every scale, eventually there must be a completely flat, absolutely silent state. But nature answers never. And the most striking evidence for this comes from the Casimir effect, predicted by Hendrik Casimir in 1948. In this experiment, two flat metal plates are placed extremely close together, just a few tens of nanometers apart. Intuitively, if there's nothing between them, no force acting, the plates should remain still. But what happens is the complete opposite. The two plates are pulled toward each other, not because of magnetic fields, not because of electric charge, not because of gravity, but because the vacuum between the plates fluctuates less than the vacuum outside. Electromagnetic fluctuations in unrestricted space are not cancelled, but they are restricted by the distance between the plates. And when outside fluctuations are stronger than inside ones, the difference in quantum pressure creates a force pushing the plates together. In other words, vacuum is not empty at all. It has energy, it has fluctuations, it has a life of its own. You cannot turn off vacuum, just as you cannot turn off electron vibration. Vacuum is the background of the universe, but it's not a still ground. It's an ocean always rippling, and it's those background ripples that lead us to another limit on material size. Because if space is always fluctuating, if quantum fields are constantly surging and subsiding every instant, then matter cannot exist at sizes smaller than those background fluctuations. You cannot build a house smaller than the vibration of the ground, just as you cannot keep an atom smaller than the amplitude of vacuum fluctuations. Even if you remove every bit of energy from an atom, cool it to the extreme limit, the vacuum itself still blows unavoidable vibrations into that atom. So even when electrons try to squeeze closer to the nucleus, they are pushed back by the vacuum's background rumble. Every virtual photon born and annihilated in the vacuum carries a little energy, a little momentum, and those fluctuations resonate throughout the entire quantum structure. This isn't just about electron vibration. It's about vibration of the very space containing the electron. And when the foundation vibrates, you cannot force matter to stand still, much less force it smaller than nature's limit. This leads us to an astonishing truth. The size of atoms, molecules or matter in general, isn't determined only by their internal forces, but also by the vibration of the cosmic background. If vacuum were completely still, matter could collapse into ultra-small points. But vacuum isn't still. It fluctuates at every frequency, creating a continuous quantum pressure background that resists matter's collapse. This is exactly why material structures have a minimum size, not because they refuse to shrink, but because the space-time background vibration doesn't allow shrinking below its quantum rhythm. Imagine trying to build a building on ground that constantly shakes. You can lay a solid foundation, but you cannot build smaller than a certain scale, because the shaking would destroy the structure. Atoms are the same. From a quantum perspective, vacuum isn't a silent wall. It's a roof whistling with wind, and matter must be large enough to exist in that environment. So every particle, every molecule, every atom is larger than the background vibration of vacuum itself. If you try to shrink an atom to a scale where background fluctuations dominate, the atom ceases to be an atom. It becomes an unstable mess of wave functions, knocked around by the universe's very backdrop. And since vacuum fluctuations are endless, happening all the time everywhere, this limit isn't optional. It's law. It's that invisible rhythm that keeps matter from sinking into nothingness. It doesn't allow matter to stand still. It doesn't allow matter to be smaller. It doesn't allow matter to go below the background resolution of the world. And thanks to that, the universe has structure, and we have a shaped world to exist within. Once we've seen that vacuum is never static, that atoms vibrate continuously, that every measurement is an intervention, and every size is quantum locked, we reach a conclusion I always find both beautiful and amusing. At the small scale, you don't control by giving orders. You control by creating the conditions for the system to choose the behavior you want. This is where quantum physics resembles the art of raising fish more than mechanical engineering. You cannot tell an electron, hey, stand still there, or move a little to the left. Electrons don't listen to you, don't care what you want, don't even have the classical concept of moving. They only obey energy structure, wave function shape, and the environment you place them in. So controlling the small world isn't imposition, it's context adjustment. You change light, magnetic fields, electric fields, temperature, and the electron responds because that's what nature requires it to do. You're not forcing, you're building the road, and the electron follows it. To see how beautifully this principle works, look at optical tweezers, the technique that won the Nobel Prize in 2018. Thanks to Arthur Ashkin, optical tweezers don't grab objects with fingers or needle tips. They use light. It sounds strange, but light has momentum, and an intensity gradient in light creates a force strong enough to hold and move tiny particles, even atoms, ions, and biological molecules. When you focus a very intense laser beam into a region, small particles are pulled toward the brightest spot, not because light pulls like a string, but because the imbalance in photon pressure on either side of the particle makes it drift toward higher intensity. You're not ordering the particle to stay there. You're creating an energy valley, and the particle falls into it, because that's the lowest energy place, and that is exactly nature's language. Optical tweezers aren't some unnatural technology. They're perfect proof that control at the atomic scale is an art of environmental tuning. You place the particle in a potential you designed, and the particle chooses the most stable state within that potential. It's not a robot taking commands. It's a musician playing according to the rules of the instrument you hand it. And this reflects a deeper principle. Control is about building the right constraints, not forcing the system to behave against its nature. An electron in a quantum box will jump into fixed energy levels. You don't force it. You build the walls and it chooses the fitting melody. An ion in a Paul trap is held not because you grab it, but because the oscillating electric field creates an average valley. It can't escape. An atom in an optical lattice moves in potential wells created by laser interference. You don't grasp the atom. You draw an energy map and let it choose its path. Quantum control isn't attack, it's persuasion. And this is exactly why control at the small scale has limits. You cannot create a stable environment for an electron to exist at a size smaller than quantum mechanics allows. You cannot create an energy valley with resolution finer than vacuum fluctuations. You cannot design a context for matter smaller than where wave functions have meaning. Control depends on three things: environment, information, and stable state. If any one is removed, like when size drops too small, control becomes meaningless. You cannot control what you cannot measure. You cannot control what has no stable state. You cannot control what is already destroyed by placing it in the environment. And so, just as every previous part has shown, we see a common law becoming ever clearer. Matter can only be controlled when it is still large enough to have a state, large enough to have a stable wave function, large enough for context to guide it. Go below that level, and you don't have an obedient electron. You have turbulence, no structure, only vibration, no predictable behavior, only probabilities blown apart by the vacuum background itself. So control at the small scale isn't like steering a wheel, shifting gears, or programming an industrial robot. It's like shaping the terrain for a tiny stream of water. You cannot tell the stream where to go, but you can place a small wall and let it flow according to natural law. And just like water, small particles don't argue with you. They simply do exactly what they must do when placed in the right context. If, at the small scale, control means creating conditions rather than imposing, then at extremely high energy scales, nature is even more blunt. If you try to force matter smaller than the size it is naturally allowed to exist at, matter doesn't shrink, it turns into something else. This isn't a metaphor. This is what happens every day in the world's largest particle accelerators. At our SLAC National Accelerator Laboratory, beams of electrons are accelerated to near the speed of light and smashed into targets to probe deep internal structures. At CERN, especially in the gigantic ring of the Large Hadron Collider, protons are accelerated to such high energies that each collision creates a miniature laboratory simulating conditions that existed only fractions of a second after the Big Bang. Those places are like gigantic microscopes that don't use light but use energy to peer into the structure of matter. And the fascinating thing is, the only way to look at smaller sizes isn't to shrink the object, but to increase the energy enough to break it apart. When you ramp up the energy of a proton and smash it into another proton, you don't see the proton shrink under the pressure of energy. Quite the opposite. The proton explodes. It isn't a solid little ball. It's a bag of energy held together by gluons containing 3 valence quarks along with hundreds of virtual quark gluon pairs constantly popping in and out of existence. When the collision energy exceeds the binding strength of the strong force, the proton no longer maintains its structure. You transition matter into an entirely new phase called quark-gluon plasma, a super-hot liquid where quarks are no longer confined inside protons but float freely in a sea of gluons. And this reveals a blunt truth. You cannot squeeze a proton smaller than its natural structure. If you try to compress a proton by packing energy into it, you don't make the proton smaller. You make the proton stop being a proton. There is no smaller version of a proton, only a broken version of a proton. This is what happens. Every time you dump enough energy and matter doesn't contract, matter changes phase. Just like you can't squeeze water into an infinitely small water. You can only turn water into plasma if you keep compressing and heating it. Physicists at SLAC once fired electrons into protons to measure its hardness. They found no solid core inside, no hard nucleus, no nucleus of the nucleus. Instead, the proton is a dynamic structure of quantum fields and particles, and its size is determined by energy oscillations and the constraints of the strong force. You cannot compress oscillations. You can only overcome the binding and shatter the structure. Experiments at CERN go even further. When 2 heavy ions like lead or gold are accelerated and collided at TeV energies, they don't just break into quark-gluon plasma. The plasma is so hot that almost no structure can survive. The system doesn't shrink under pressure. It melts back into the primordial phase that existed before protons or neutrons appeared in the young universe. So what does this say about the limits of matter? It says that below its natural size, matter cannot maintain structure, not because technology isn't advanced enough, but because below that limit, there is no structure left to maintain. A proton isn't a box you can compress from 1 unit to 0.5. It's a dynamic energy system, and its size is exactly the minimum size. The strong force can hold its configuration together. Trying to shrink below that is like trying to compress a water balloon with infinite force. You don't make it smaller, you make it burst. And this is the most important point. Matter collapses into a new phase before it ever has a chance to become infinitely small. There is no infinitely small proton, no infinitely small atom, no infinitely small molecule. Below that quantum threshold, matter doesn't contract, doesn't shrink, doesn't obey. It changes phase, becomes a different form of energy. The universe seems to be telling us, if that size isn't enough to exist, then I won't allow structure to exist anymore. I only allow energy. And this is the most powerful proof that the question, can matter get so small? It's uncontrollable, has never been on target. Matter never gets that small. Before it reaches that anomalous limit, it has already disintegrated, changed. becomes something entirely different, to which the concept of controlling matter no longer applies. All that's left is pure energy. And if the proton exploding in accelerators shows us that matter cannot be squeezed smaller than its natural structure, there is an even deeper truth, one that almost flips all our intuition upside down. When energy is high enough, matter doesn't shrink, it disappears. It doesn't contract into a smaller particle. It transitions into pure field, and from field it can give birth to new matter. This isn't philosophical metaphor. It's something that happens routinely, almost routinely, in high-energy physics. Look at pair production, where an extremely high-energy photon, when passing close to a nucleus, can split itself into an electron and a positron. The positron, the antiparticle of the electron, was first observed by Carl Anderson in 1932, and that discovery immediately revealed that E equals sine mc Guedet isn't just a pretty formula on a classroom wall. It's the operating law of reality. Energy can become matter, and matter can dissolve into energy. When a photon has enough energy, it doesn't shrink into a denser photon. It changes phase and appears as an electron and positron, two particles with real mass. And this leads us to an inescapable conclusion. At sufficiently high energy, matter no longer holds any shape or size. It is only oscillation of fields. The interesting thing is that the reverse process also happens an electron and positron, when they meet, can annihilate and turn into two photons, two entities that once had finite size, once were particles, once had their own wave function shapes, now dissolve into light back into electromagnetic field oscillations. When you increase energy, matter doesn't compress like a sponge. It becomes too energetic to maintain its old form, and energy forces it to transition into something else. E equals sine mc Guedet isn't just describing equivalence between energy and mass. It describes the fundamental exchange between field and matter. From this perspective, every particle we casually call matter is just a specific stable way quantum fields behave at a certain energy level. When that energy changes, the stable configuration vanishes and the particle disappears. So what happens when you try to force matter smaller than its natural size? You don't create a smaller version. You destabilize the energy and cause matter to change phase, melt into field. If you try to shrink a proton by dumping more energy into it, the proton doesn't become a mini proton. It breaks into quark gluon plasma. If you try to shrink an electron, you can't, because in the standard model the electron is a point particle. But when you supply energy beyond the threshold, you create new particles, not a small electron. And if you try to squeeze any particle by packing energy into a point, you'll soon generate so much energy that it no longer makes sense as particle size. It becomes the condition for creating new particles. Thus, high energy doesn't lead to smaller matter. It leads to less matter and more field. The microscopic world doesn't shrink according to your wishes. It transforms according to nature's rules. And when you look at this, the entire idea of matter getting so small, it's uncontrollable, collapses for one simple reason. Matter cannot maintain a state in order to become smaller. When you push it beyond the stability range, you no longer have matter. You have field, something without shape, without size, without structure to control in the way we understand. This is like trying to squeeze a water droplet smaller than its molecule. At some point, it ceases to be water. Or trying to compress a spring to zero length, it ceases to be a spring. It breaks at extreme energies. Matter ceases to be matter. It becomes pure oscillation of fundamental fields. And this is the crucial point. When matter can no longer hold structure, the concept of control vanishes along with it. You cannot control something without boundaries, without stable states, without size in any meaningful sense. An invisible photon has no position to control. A quark gluon plasma has no shape to hold, and a pure field state has no path to predict. At high enough energy, matter refuses the notion of smaller still. It chooses another path, becoming field, and that is the definitive end to any idea that matter could become so small it escapes our ability to control it. Not because we are weak, but because matter does not exist in that form. Once you've seen matter melt into field, seen protons shatter into quark, gluon plasma, seen photons turn into electron, positron pairs and back again, you begin to understand that the microscopic world isn't a free-for-all playground. It's tightly held by an absolute set of rules. One of the clearest proofs is the very existence of the hydrogen atom, the simplest yet most fragile building block of the universe. Hydrogen exists because a series of physical constants have values so precise they make you shiver. Consider the electromagnetic force which binds the electron to the proton. The strength of this force is described by a strange number called the fine structure constant, with an experimental value of approximately 1/137th, not 1/100th, not 1/1000th, not any other number, precisely 1/137th. If that number deviated by just a few percent, atoms as we know them would not exist. If the electromagnetic force were much stronger, the electron would be pulled too close to the proton. The ground state energy would become too deep, and the atom would lose stability. The electron would fall into the nucleus or exist in a state where molecules could not form. If the electromagnetic force were slightly weaker, the electron wouldn't be held tightly enough. Atoms would become so loose that all chemical bonds would collapse. Hydrogen would not be stable. Helium would not form. And the complex chains of carbon chemistry would never appear. A small change in that seemingly simple constant could turn the universe into a scattered sea of particles, unable to connect. What does this mean? It means nature doesn't just set size limits for matter. It sets a hard format for the existence of every structure. Hydrogen doesn't choose a radius of about 0.05 nanometers. It's because the electromagnetic force is just strong enough to hold the electron in a stable region when balanced against quantum vibrational energy. Carbon molecules don't like tetrahedral shapes. It's because physical constants force electrons to distribute into specific orbitals. Protons don't have a size of approximately 0. 8 femtometers because it's convenient. It's because the strong force pulls quarks exactly to that extent and allows nothing else. Nature has selected an extremely narrow set of values for these constants, and that very set creates room for matter, molecules, and life. If even one of those constants shifted slightly, the fine structure constant, electron mass, proton mass, Planck's constant, speed of light, hydrogen would lose stability, molecules would cease to exist, stars would not burn, and the universe would have no chance to form any structure. When viewed this way, we see that matter isn't something that can freely shrink or expand. It's locked into an extremely narrow band of universal constants. Step outside that band, and matter ceases to exist. It doesn't shrink into a different version. It vanishes from the map of reality. This explains why, from the very beginning, every attempt to shrink matter has led us back to the same answer: impossible. Because not only quantum structure, electromagnetic force, strong force, but the very foundational constants of the universe all unanimously declare, this far and no further. Matter can only exist in a space that the physical constants support for existence. Step outside that boundary, and you no longer have matter to control, no atoms to compress, no molecules to arrange. You only have field and floating energy. And that is the sign that nature doesn't merely limit matter, nature formats matter. And now, having traveled through hydrogen, chemical bonds, Coulomb force, strong force, vacuum background oscillations, pair production, and quark, gluon plasma. One final big picture emerges clearly. Matter is never too small to control, because it cannot become smaller than the boundaries nature has erected. 5 foundational principles: quantization, uncertainty, zero-point vibration, the Planck limit, and force balance are 5 physical walls no one can cross, not even nature itself. Quantization says energy has discrete steps and cannot drop below the ground. State electrons cannot fall into the nucleus. Atoms cannot shrink below their minimum vibration speed. The uncertainty principle says you cannot squeeze matter into a region so small that both position and momentum or defined background vibrations will surge and shatter every attempt to compact. Zero-point vibration says atoms always oscillate. Even at 0 Kelvin, you cannot compress them into a smaller region without destabilizing the system and causing it to bounce out. The Planck limit says space-time has a minimum resolution. There is no spatial address smaller than that to place matter into below that. The concept of position becomes meaningless, and force balance between Coulomb attraction and quantum repulsion, between strong force and electromagnetic force, erects the fixed sizes of atoms and nuclei compressing below that. Doesn't make matter contract. It makes it melt into another phase. These 5 principles don't operate separately. They are like 5 layers of reinforced concrete stacked on top of each other, locking matter into the range where it can exist, and precisely the range where we can control it. You cannot control matter smaller than the point where nature itself can no longer define it. You cannot control something without size, without state, without a stable wave function. But this isn't bad news. It's wonderful news, because precisely because matter cannot shrink infinitely, we have a world, durable atoms, stable molecules, solids, liquids, gases, biology, chemistry, nanotechnology, 3 nanometer transistors, instruments precise enough to move individual atoms. If matter could shrink infinitely, all of that would vanish. Matter would collapse into an energy sea with no structure to control. Nature erects limits, not to hinder us, but to create a playing field where matter has shape and where control has meaning. Therefore, when people ask, is there a threshold where matter becomes too small to control? The real answer is never. Not because we are clever enough to control everything, but because matter cannot shrink beyond the region where control still has definition. Matter always stops exactly at the size where nature can still describe it. And precisely because it can be described, it can be controlled. The limit of control is not size. It is the existence of stable states. Matter cannot be smaller than its final stable state. And as long as that state exists, you can always design environments, create potentials, adjust light or magnetic fields to control it. The question isn't, is matter too small, but rather, does natural law permit matter to exist in order to be controlled? And wherever matter still exists, control is always possible. After passing through all the walls nature has built, from quantization, uncertainty, background vibration, the Planck limit to force balance, we look back and realize something perhaps no one expected at the beginning. Those limits are not shackles that impoverish the universe. They are the very foundation that allows the universe to exist. If electrons were not bound to discrete energy levels, atoms would have collapsed. If atoms did not vibrate with zero-point energy, matter would have collapsed into meaningless points. If vacuum had no background rumble, no atom could maintain shape. If the Planck length did not set a lower bound for space-time, size would cease to be a concept, and matter would have nowhere to stand. And if the strong force, electromagnetic force, and quantum rules did not hold exactly the values the universe selected to many decimal places, hydrogen would not be stable, molecules would not form, stars would not burn, and life would have no place to try its luck. Sometimes we think limits are barriers, things preventing us from doing the impossible. But at the atomic scale, it is the limits themselves that make anything possible at all. Matter exists only because nature said, this far is enough. It endures only because nature does not allow it to be smaller. The stability we enjoy, from water molecules to DNA, from 3 nanometers transistors to intricate biological structures, can only appear because matter cannot leave the minimum size it is permitted. If matter could shrink infinitely, if electrons could fall into nuclei, if protons could be compressed to 0 size, if molecules could be squeezed until shape dissolves, then our universe would not be a structured world. It would be a blind sea of energy, with no atoms, no molecules, no chemistry, no life, nothing to control, and no one to control it. Therefore, when we say matter is never too small to control, we are not merely saying our technology is good enough. We are saying nature has set a minimum size so that matter itself can exist. Control is not just a technical achievement. It is a privilege granted by the structure of reality itself. And is there anything more beautiful than realizing that the universe isn't making things difficult for us, but quietly creating a range where control is possible, where the small world doesn't escape our hands, yet doesn't shatter when we approach it? By erecting limits, nature has created a complete playground, stable enough to exist, flexible enough to explore, strange enough to challenge, and rational enough for us to understand. So after all these journeys through quantum mechanics and the deepest structures of matter, perhaps the final question is not how much smaller can we make matter, but one I believe every scientist quietly whispers in their mind. If nature sets limits so that matter can exist, then what limit is waiting for us to discover next? Subscribe so you don't miss the next parts of this journey, exploring the universe at its deepest levels. See you again in the next scientific adventure, where we open yet another new door into reality.